Okay, so now let me discuss subgame perfect equilibrium in the quantity competition game, where firm 1 chooses the quantity first, and then firm 2 is going to observe what firm 1 has done and is going to choose a quantity. So this is known as Stackelberg duopoly model. Okay, Stackelberg duopoly model. So again, if you recall, player 1 has, so what are the set of strategies that player 1 has? It's R plus. Okay, so he can choose any of the number from R plus. So that's a strategy for player 1. Okay, so he's going to choose a quantity. So he can choose any real number. Okay, any non-negative real number. That's his strategy set. What about player 2? What about player 2? So what are the, so give an example of a strategy for player 2. So like, for example, a strategy for player 1, example of a strategy of player 1 is he can choose output 2. Okay, that's an example. He can also choose output 2.9. That's also an example. So this is a different strategy, this is a different strategy. So all these are different strategies for player 1. What about player 2? Give an example of a strategy of player 2. What do you think? Exactly, he's going to supply a function of q1. Very good. Okay, that's exactly what a strategy is for player 2. Okay, so this is a set of all strategies for player 1. You can call this the choice set or the strategy set or whatever you want to call it, set of all plans basically. Okay, and what is the set of all strategies of player 2? It is not R plus, it is a function. Okay, set of functions. So it is a set of functions from R plus to R plus. So he's going to choose one of the functions. Okay, so suppose you have the following situation. We are given the inverse demand function. Okay, and for the time being, let's keep the costs 0. So C1 Q1 is 0 and C2 Q2 is 0. Okay, so you have this data. Okay, now what you have to do is you have to find the subgame perfect equilibrium. So how will you approach? First, you will solve all subgames of this type. These little games where player 1 has already moved, and then player 2 is going to make a move. So what do you think player 2 is going to choose? How is player 2 going to play this game? So basically, first we'll have to figure out in the backward induction procedure, how is player 2 going to play, right? Because this is exactly what is going on here. We are going backwards. We are first solving these games, and then we are going to solve this whole game. Okay, and player 1 is going to take into account how player 2 is going to play at each of these points, and then decide his q1. Okay, so can you tell me how will player 2 play this game? We have already solved this game actually. When we were solving for Cournot equilibrium, we already know how to figure out player 2's strategy. Suppose he observes q1. Player 2 is going to choose what here? Exactly, his best response. So you already know that. Okay, I mean, it's the same thing. Okay, so we know how to figure out the best response function. So what is the best response? So first of all, let's figure out the best response function. BR2 Q1 is equal to, I think it is 12 minus Q1 by 2. Just check. So this is the best response if Q1 is less than 12. Okay, and if Q1 is greater than or equal to 12, then he can choose R plus, in R plus. Now, you should be a little careful. You know, there is a difference between the strategy and the best response. So strategy is you are going to program the computer and tell the computer, okay, this is how you're going to play. So if you see, this is okay. You can say that, okay, if Q1 is less than 12, this is how you want to play. But if Q1 is greater than or equal to 12, you're not going to say that, okay, play R plus. You have to tell the computer what quantity, do you want computer to choose in each of these situations. So like, for example, if Q1 is 13, you have to tell the computer, you have to tell the plan. Okay, so you can, because all these are best responses, so you can choose any of them. Okay, you can choose any of them. It's completely fine. The way you want to choose, you can choose. It's completely okay. You can choose 14, 15, 20, 1,000, 10,000, whatever you like. You can write the best you can write the strategy in any way. Okay, so one possible strategy is Q2 Q1 is equal to, so this is a strategy, this is an example strategy which will work, you know, if you're finding the subgame perfect equilibrium. You know, there are more, but this is one of them. So it is 12 minus Q1 by 2 if Q1 is less than 12. Okay, notice that this is a strategy. Okay, this is the best response. Okay, it's a set of best responses. Here it's a function. Okay, it's a function. It means that you know, for every action of player 1, there is exactly one action that player 2 is choosing. Okay, so Q2 as a function of Q1 is 12 minus Q1 by 2 if Q1 is less than 12, and Q2 as a function of Q1 is, let's say, as Siddharth said, you know, you can choose 0, for example. You can choose anything, but let's say you choose 0. If Q1 is greater than or equal to 12, player 2 decides to choose 0. Okay. Okay, so now we have already solved this game from player 2's perspective. So basically we have solved this game everywhere here. Okay, at all these points we have solved this game. Now we're going to solve this big game. Is that okay? That's the next step. So player 1 is obviously he'll be able to guess that this is how player 2 is going to play. So player 1 is going to take this into account and choose his best action. Okay, so player 1 will maximize with respect to Q1, okay, his own profit. Okay, what is his profit? Max of 12 minus Q1 minus Q2 comma 0, that's the price, times the quantity, that's the total revenue, minus the cost, which is 0, subject to a constraint that Q2 is related to Q1 in this way. Okay, so which means that if you want, you can write it like this: Q2 is max of 12 minus Q1 by 2 comma 0. Okay, so player 1 will solve this game, will solve this optimization problem. Okay, again, it's not a difficult problem, it's very simple. It's an one variable optimization problem. You just have to see what's going on here. So if you can just check, what if you play more than 12? What if you choose Q1 to be more than 12? If Q1 is more than 12, then Q2 will be 0, and then this price will be 0, and if price will be 0, then revenue will be 0. So I know that my payoff profit from playing Q1, okay, is 0 if Q1 is greater than equal to 12. So definitely I'm not going to choose, choose that because I can do better. Okay, how can I do better? Well, I can choose Q1 less than 12. If I choose Q1 less than 12, then player 2 will choose 12 minus Q1 by 2. If player 2 will choose 12 minus Q1 by 2, then 12 minus Q1 minus 12 minus Q1 by 2 will be 12 minus Q1 by 2. So the price will be 12 minus Q1 by 2, which is positive because Q1 is less than 12. Okay, and since Q1 is positive, I'll get a positive revenue or positive profit in this case. Okay, so therefore any output greater than or equal to 12 is impossible. He's never going to choose that because he can always make positive profit by choosing an output between 0 and 12. Is that clear to everyone? Yes. So I know I just have to solve this optimization problem actually, because I'm never going to choose above 12. I can write this problem in a simple way. It's a closed interval method, and then I can apply that to solve it. So if Q1 is between 0 and 12, I know that this is positive, right? Okay, if Q1 is between 0 and 12, this is positive. This is positive. The max of these two will be this. So I know Q2 is this. In that situation, Q2 is this. So I can write this as max of 12 minus Q1 minus Q2, which will be 12 minus Q1 by 2, comma 0 into Q1. And because Q1 is between 0 and 12, this term is actually 12 minus Q1 by 2. Because 12 minus Q1 minus 12 minus Q1 by 2 is 12 minus Q1 by 2. So this term is also positive. So I can also drop this max. Okay, and I'm going to get this problem. This is straightforward, right? Okay, this is a nice concave function. And all that you have to do is take the derivative, set it equal to 0, and you'll figure out that the solution, when you're going to take the derivative, set it equal to 0, lies in this interval. And since it is a concave function, that local maximum will be a global maximum. So you don't even have to look at the corners or the boundaries, because I've already told you if it's a concave function and it satisfies the first order condition in the interval, then it's a sufficient condition. It's also a guarantee that it's a global optimum. So yeah, so just let's just quickly do this. 12 by 2 minus so what is the derivative of Q1 square? It is 2Q1, and that's just going to cancel with 2 in the denominator. So you'll get Q1 equal to 6. So that is the strategy of player 1. Is that okay? And strategy of player 2 is Q2 equals max of 12 minus Q1 by 2 comma 0. Okay, so this is the strategy of player 2. Okay, it's a function. So this combination is a subgame perfect equilibrium. Okay, this and this is a subgame perfect equilibrium. Subgame perfect equilibrium. Okay, and what is the subgame perfect equilibrium outcome? Subgame perfect equilibrium outcome is 6 comma. So what is the path, outcome path? So if he produces 6, player 2 produces 12 minus 6 by 2, which is 3. Okay, so this is the outcome. And what are the payoffs? So subgame perfect equilibrium payoffs are, so what are the payoffs? You just have to find the profits. That's it. Okay, you just have to find the profits. Well, if this is 6, this is 3, this is the quantity chosen by firm 1, this is the quantity chosen by firm 2. So the total quantity is 9. So the price will be 3 because it's 12 minus Q. So price is 3, so this is 18, and this is 9. Okay, so these are the payoffs.